Okay, I think we're ready. So I'm going to get started. I'd like to welcome everyone to the Thursday session of the 2021 EGMAC. This is a session on radiation and aerosols. I'm Patrick Sheridan, work in the Global Monitoring Laboratory. Just have a couple of things to go over with you guys. Apologies to the ones that have been here in previous days because you've heard it all before. First of all is to any of the other panelists or organizers, please mute your mic when you're not actively speaking. On a lot of computers, the microphone and the speaker are close to each other, so we get a lot of feedback there. Next, the GMAC website is where you'll go to basically look at for any of the logistics of the conference, how to get to the different meeting rooms, how to get to the Slack channel, how to get anywhere basically. So that website is listed at the top of the screen you're seeing, and I encourage you to go take a look at it. My co-chairs today will be Kathy Lance, who is going to be monitoring the questions in the GoToMeeting, and Lauren Schmeisser, who will be monitoring any questions or comments that are put into the Slack workspace. So after a talk is finished, hopefully there'll be time for one or two questions, and we can pick a question or two out of either one of those. Remind you that every day there is a daily peer award for the best presentation. Again, the details are on the GMAC website. So we'd encourage you to go and visit the poster presentations and listen to the oral presentations, and then put in a vote for best presentation. We're just about ready to get started with the talks. For the presenters, I'm going to keep track of time, and this is the AGU format, so it's going to be a 15-minute talk. I'm going to break in at 12 minutes and let you know that the 12-minute mark has passed, and encourage you to finish up in the next minute or two, and then hopefully there'll be time for some questions. So without further ado, we're going to get started here. The first talk is going to be given by Christoph Mank from Institute of Energy and Climate Research in Jülich, and he's going to talk about aerosol observations on the IAGOS Karabakh Flying Laboratory. Christoph, go ahead. Yeah. Thank you very much, Christoph. The next talk is by Logan Soldo, who is from GML and Ceres. And the title of his talk is Snow Extent and Depth over Central North America, 1966 to 2018. Go ahead, Logan.
Thank you. Yeah, so I'm going to be talking about snow extent and depth over Central North America between the years of 1966 and 2018. This was a part of my master's thesis under the supervision of David A. Robinson. And before we move on, I want to point out just the satellite image here in the background. Just to make note of the reflectivity and how clear it is to see on these satellite images, just the difference between the snow and the bare soil compared to the clouds. And the high reflectivity of snow. So a little bit of introduction and background. So snow depth is defined as the sum of new snow and ice plus old snow from previous storms, while extent, like we saw in the satellite image, is the area of land covered by snow. And snow is important to the local, regional, and global climates because of three factors that I want to point out. This reflectivity of incoming solar radiation, which you see here, the solar irradiance and solar reflectance, that would be part of the extent. And then it also acts as an insulator and moisture provider for the soil beneath. So this soil layer, this snow layer, will percolate water into the soil throughout the winter season instead of all at once like a rainstorm might. And you can see that the snow layer will also prevent the soil layer from being in contact with the cold air above to prevent some freezing that might occur in the soil. It also provides protection from the soil from winds. So the snow layer, once again, will protect from strong wind that might come across and blow away important nutrients that are laid over the winter. This was from Marks et al., which basically sums up very well the impacts of snow. So like I said before, snow is also highly reflective. So fresh snow has a reflectivity of about 0.95, old snow 0.4, which is still quite high when you compare it to a glacier or even grass, sand, or soil. So snow depth is also it impacts society as well. So you can imagine that snow will build up through the winter, and then in the spring, a big rainstorm will come and cause some flooding of that snow that's built up. And this is mainly true in three major rivers that we see in Central North America: the Mississippi, the Missouri, like you see here in 2018 versus 2019, the impacts that it has, and then a lesser known river, the Red River of the North, up in on the border of North Dakota and Canada, where we also see this flooding. So this snow depth is important to people who live along these rivers to know. So some data that goes into this, that went into this study, were daily cooperative observations from the United States and Canada, which were averaged within grid cells between 1966 and 2018. And this coincides with this these snow extent maps, which were taken from, so an analyst would get visual images from satellite and then trace out the snow line. But this only gives you a two-dimensional view and only tells you about extent. So we want to know more about depth. So we used station observations from the ground, and we gridded these into a Cartesian grid on a polar stereographic projection. And within this large grid, so you see there is data for this entire section, but we chose this area in particular. So zooming in a little bit, you can see the difference in area because of this projection, the area is larger in the north and smaller in the south, the grid cells. And for elevation wise, as you'd expect, elevation increases as you go further west. But for the most part, we chose this region not because it's flat per se, but because it is mostly grassland, prairie land, not so much forest that might impact the results very much. And just for a little bit of orientation, we're talking west of the Great Lakes, not to get involved with any lake effect snow, and east of the Rocky Mountains, not to get involved with any mountain observations. So some quality control had to go in. We're talking about station observations, so there's always some problems that might come about. And there was initial quality control that was done by NCEI, but some further quality control had to be done. So one of those was using snowfall data to validate the snow depth observations. So what this means is that if there was an increase in snow depth, but not an increase in snowfall, we had to remove those snow depth observations just to be consistent. And then a consistency standard was implemented by removing any questionable observations that were surrounded by blocks of missing data. So what this means is that if there was an observation on one day surrounded by blocks of missing data, the Weather Service instructs observers to report zeros on days that there's no snow. So that one day within a block couldn't really be trusted. And the results over here on the right show the results of this. So you can see that in the United States, the quality was quite good, but as you get further into Canada, it's less densely populated and you get a little bit more missing data. And this is one of the reasons why we have this sharp cutoff, because while we want to know more about what's happening near the Hudson Bay up here, the data quality was just too low to use. So a little bit about the climatology. Let me start by putting this into context of temperature and precipitation. So we're going to talk about three regions here for this slide. I'm talking about the Northern Rockies and Plains, the Upper Midwest, and the South. And this data comes from Climate at a Glance. So for the Northern Rockies, when we look at precipitation, precipitation hasn't changed all too much over the years, but temperature has increased quite a bit. As we move to the Upper Midwest, precipitation between November and April, we're talking here, has increased slightly, but not quite as much as temperature has. And in the South, we see a little bit larger of an increase, and then once again, this temperature increase. And I'll come back to this closer to the end once we see the results of the snow. So we're talking about 108 regions here. So we had to split them into 4 subregions to get a better feel for what's going on. And we did this by determining the percentage of days with depth above 7.6 centimeters between December 1st and March 31st. So subregion 1 would be covered from 0 to 25%. And then subregion 4 up here in the blue would be 76 to 100% of snow cover between December 1st and March 31st. These are just the snowy months that we're talking about. And so why do we choose 7.6 centimeters? Well, 7.6 centimeters is 3 inches, and there's at lower depths, there's observational biases that that just come with the uncertainty. So for example, here on the right, an observer would go out into this scene and they would measure 1 inch on the left, 0 inches on the right. They would average that to 0.5 and round that to 1 inch. And this is what we wanted to avoid. At 3 inches, you can confidently say that the entire grid cell at least has a cover of snow on the ground. So getting back to the regions here, we're looking at the average daily snow depth, and this shading is the 25th and 75th percentile, with the dark shading, or the dark line being the average, with snow depth on the left and the day of year on the x-axis. And so what this figure really shows is it shows that these regions are actually quite distinct. This dark blue area being region 4 and region 3 being this thin area. And even this thin area doesn't get into this darker blue area. So in region 4, we see the snowiest months being January to February, with a plateau and then a sharp drop off, while the others kind of see a peak and then a petering off as we get into the spring. So now I'm going to talk about the time series analysis. So here we're looking at snow depth at 4 different threshold depths. We're looking at it at 10 inches, 6 inches, 3 inches, and 1 inch, and just looking at the number of days that are above this threshold. And what I really want to point out here is this change per decade. And you can see that at the deepest depths, we're seeing a larger change per decade than in the smaller depths. And their p-values are quite significant. And so when we look at snow depth and extent here, we're looking at the sum of days for extent. We're looking at the sum of days above 1 inch, while on the right, we're looking at snow depth a little bit differently. We're looking at the average monthly sum of snow depth. And here, I just want to point out the change per decade once again, and just to show that the snow depth has decreased faster and more than the snow extent has. And this is particularly true in January and February, the snowiest months of the year. When we look at region 3, we're looking at this 4 different thresholds again, and once again, you can see that the change in per decade is highest at the deepest depths and decreases as you get further down, with some significant values at 3 inches and 1 inch. Looking at this for snow extent and depth, once again, snow depth decreasing faster than snow extent. Mostly coming in January and February, but in this case, we're seeing actually an increase in the shoulder months of November and April. Now moving on to subregion 2, we're seeing the same thing with the deepest depths showing the greatest decreases, and then as we move on to the extent versus depth, once again, depth decreasing faster than extent, and once again, we're seeing a slight increase in the shoulder month of April. Subregion 1, while there isn't much snow to talk about in this region, looking at the bottom 2 depths, we actually do see, once again, this change per decade being higher in the deeper depths of 7.6. And then looking again at extent versus depth, once again, there's not much to see, not too much snow into this region that lasts through the winter, but once again, depth decreasing faster than extent, and mostly in January. So some conclusions here. The results of this study, they showed that snow depth and snow extent have been decreasing, and the greatest decreases are in depth at deeper depths. So these decreases are most significant in January and February, those snowy months, and region 2 and 3 showed actual increases in the shoulder months. And this actually is consistent with what we see for the general Northern Hemisphere when you look at snow extent. So that made sense. And All the subregions, though, they showed a decrease in the number of days with snow cover at various depths. And then getting back to those temperature and precipitation graphs, we're actually seeing that precipitation overall isn't decreasing. We saw it increasing in some places, while we see snow depth now decreasing. And we didn't look into this, but this could be a result of perhaps a changing phase. So maybe we're getting more rain instead of snow. Or maybe snow depth just isn't surviving the warmer temperatures. Thank you.
Okay, thank you, Logan. That was very, very interesting, and you're right on time. Do we have any questions?
No questions in the Slack.
Okay, well, I have a question for you, Logan. Maybe I just missed this, but how were those regions and sub-regions chosen? And I guess I'm a little bit disappointed that the Front Range of Colorado was not included in that. It shows the edge of one of your boxes is right on Cheyenne, but boy, it would have been interesting if we could have gotten the Front Range of Colorado into that, because you would have gotten, you have very good meteorological observations there with Boulder and Fort Collins in that region. And you would also get a lot of data in April and even into May. So what would you, how would you answer that?
Yeah, so there was a few reasons for that. One being that was just the data quality, and speaking of the Front Range, we don't have that issue, but also the size of the cells. We really wanted to avoid the impacts that mountain snow might have, because it's just completely different. And we talk about observatories, it might, having half the cells in the plains area of the Front Range and then some in the mountains might not be justified, and it might not represent the entire cell well. So here we wanted to just have a fine divide of similarity in terrain, really.
Okay, do we have any more questions?
Yeah, I have one question here for Logan, and that's, how do these trends project over time? And at what point are the changes in albedo worrisome? And I actually, too, am going to add just a little bit in terms of those trends project over time. I was kind of curious to see, do you have a numbers for as it goes between those subregions for that snow depth trends?
Yeah, so projections, I'm not sure about. It's hard to say what the future will hold. And what was the second question?
Yeah, it was, how do these trends project over time, and at what point are the changes in albedo worrisome? And
Well, the thing about this is that the changes in albedo, so because we aren't seeing those changes in extent so much, I wouldn't say it's so much a problem of worrying about albedo, but worrying more about the water resource side of things, because we're still getting snow as we once were, but we aren't getting as deep of snow.
okay, thank you. And just curious, so how much is what are those trends from region to region? So it looked like the slopes were steeper, the further north. What were those trends in numbers?
Yeah, I don't, so we just did it in decade, just to change per decade up here. Yeah.
8%. And what was subregion? The
Sorry.
next one, 8% to.
So 9%. So yeah, so
okay.
when we talk about the change per decade, I mean, we're only talking about 2 days per decade, but this over time could be quite significant, because we're talking about from the start of the period to the end of the period, talking about 20 days. Yeah.
Great, thank you.
Yeah.
Hey, thank you, Logan. Very, very nice.
Thank you.
So the next talk will be presented by Kelly Balmes, who is also from GML and from Ceres. Title of her talk is All Sky Aerosol Radiative Effects at the ARM SGP site. Go ahead, Kelly.
Great, thanks. Can you hear me and see my slides?
Yes.
Cool, thanks. Hi, yes, I'm Kelly Baums. I'm a new postdoc in the GRAD group here at GML. And today I'll be talking about part of my PhD dissertation, which I defended almost 2 months ago at the University of Washington with my advisor, Chung Fu. And today I'll be presenting on one of the chapters, which was the all-sky aerosol direct radiative effects at the ARM SGP site. First, let's start with how aerosols influence the climate system with this schematic from the IPCC report, where the first category is the aerosol radiation interactions, including the direct effect, which is the direct scattering and absorption due to aerosols, as well as the semi-direct effect or adjustments due to this direct effect. In addition, there's aerosol cloud interactions, which include changes to the cloud albedo from aerosols, as well as adjustments to that. But all the way back to the start, we see that the aerosol direct radiative effect is the most fundamental understanding of aerosols in the climate system. And by increasing knowledge of the aerosol direct radiative effect, which is due to both natural and anthropogenic aerosols, this can lead to a constraint on the direct radiative forcing or the forcing due to anthropogenic aerosols alone. In order to quantify the aerosol direct radiative effect, is calculated by considering an atmosphere with and without aerosols. So imagine we have an atmosphere here on the left where we have aerosols. Then we have a downwelling flux at the top of the atmosphere, or the TOA, and an upwelling flux, as well as a downwelling and upwelling flux at the surface. Then we can run a radiative transfer model with and without the aerosols in order to isolate the impact of the aerosols. And this can be represented by the equation we see at the top here as the change in the downwelling flux at the TOA and the upwelling flux of the TOA with and without aerosols. We can also do this for using the fluxes at the surface in order to get the surface aerosol direct radiative effect. In order to run the radiative transfer model, I need to know several different things, including the aerosol optical properties, such as the aerosol optical depth, as well as the scattering and absorbing properties of the aerosols, as well as the cloud distribution, the surface properties, the atmospheric state, as well as the sun-Earth geometry. However, it's difficult to have all this information on the global scale. And recent global estimates of the TOA all-sky aerosol direct radiative effect is about -2 watts per meter squared. However, many of these studies rely on the Cloud Aerosol LiDAR and Infrared Pathfinder Satellite, or CALIPSO, which recent studies have suggested that the detection sensitivity of CALIPSO is not enough in order to detect all radiatively significant aerosols. And this has implications in that it limits the aerosol direct radiative effect accuracy. So since CALIPSO misses some aerosols, this leads to a low bias in the AOD and ultimately a low bias in the aerosol direct radiative effect. With one such example in Thorson and Fu 2015, which we see in the figure on the right over here, where ground-based LiDAR estimate is shown in the darker shading, and estimate from CALIPSO is shown in the lighter shading for the TOA on the top and the surface on the bottom. And when we compare the CALIPSO estimate to the ground-based estimate, we see that it's biased low at both the TOA and the surface. Ground-based sites provide long-term continuous measurements that provide the opportunity to estimate the regional aerosol direct radiative effect with all quantities from observations. And then this can provide a benchmark that can then inform satellite and modeling global estimates. In this study, we'll be looking at the Atmospheric Radiation Measurement Program, or ARM, which provides high-quality cloud, aerosol, and radiation observations. And we'll be looking at the Southern Great Plains site, or SGP, located in Oklahoma in the central US. And the first part of this project was published on the Clear Sky Aerosol Direct Radiative Effect earlier this year. And then the second part of the project is in revisions on the all sky, which is including both the clear and cloudy sky aerosol direct radiative effect. And this will be the focus of the talk today. So the primary instrument that we'll be using for aerosol and cloud observations is the Raman LiDAR, which operates at 355 nanometers. The data product we'll be using is the Feature Detection and Extinction, or FEX for short, which combines multiple channels and thermodynamic state from radiosondes in order to detect and classify features and then retrieve extinction. We'll be using a resolution of 10 minutes and 30 meters with about 8 years of data from August 2008 to August 2016. And then an example of the data from this data product is seen on the left here, where we have the feature type on the top plot as a function of time and height, where the aerosols there are denoted in the gray, ice clouds in black, and the liquid clouds in red. And then on the bottom plot, we have the particulate extinction for the given features that were detected for this day. Other data products we'll be considering are from the Aerosol Robotic Network, or AeroNet Sonophotometer, which will provide AOD, single scattering albedo, and asymmetry factor at several different wavelengths. And when the Raman lidar fully attenuates, which is denoted by this light blue on the x-axis, which is when the Raman lidar cannot observe all the way to the top of the profile, we bring in radar cloud profiles using the Ka-band arm zenith radar, or KZR, as well as the millimeter wavelength cloud radar, or MMCR. And then this is further constrained to the microwave radiometer when available. So the last slide gave a sense of the aerosols for one day, but to get a sense of the aerosols across the whole time period at SGP, here we consider monthly climatology of the aerosol extinction vertical profiles. So on the x-axis, we have the aerosol extinction at 355 nanometers as a function of height on the y-axis for each month, starting in January on the left to December on the right. And then the black line is indicating the mean extinction profile, and the shading is the 25th to 75th percentile. And so at SGP, we see that the aerosols are closer to the surface in the winter and higher up in the atmosphere from about May to September. And this corresponds to a larger AOD in the summer and a smaller AOD in the winter. So now that we've introduced the data, we want to test and validate the model and observed inputs by comparing with observed fluxes through a radiative closure experiment. So the basic premise is that we input the observations into a model. In this case, we're using the NASA Langley Foulial radiative transfer model. And then we get modeled flux output. And in this case, we'll be looking at the downwelling surface shortwave fluxes in terms of the total, as well as the direct and diffuse components. And then we can compare these fluxes with observations from the surface radiometers and the ARM QC-RAD dataset to see how the observed inputs and models are doing. So now looking at the radiative closure experiment results, where we have the observed flux on the x-axis and the model flux on the y-axis for the total surface downwelling flux on the left, and then the direct component in the middle and the diffuse on the right in terms of frequency plots. First, looking at the clear sky in the top panel here, we see that the observed fluxes and model fluxes agree within 1 watt per meter squared, which corresponds to a relative difference of 0.5% or less for the total direct and diffuse. Next, looking at the cloudy sky in the middle panel for the transparent cloudy sky, or when we're using the Raman lidar cloud retrievals. And then on the bottom, the opaque cloudy sky, or when we're using the radar cloud water content profiles. And we see that the relative difference for the total flux for both cloudy sky situation is about 6 to 7%. And so overall, we see agreement between the observed and model fluxes, and this validates the model and observed inputs. So now that we have validated the model and observations, we want to quantify the aerosol direct radiative effect since we have confidence in both. So recall the instantaneous aerosol direct radiative effect was by considering how the fluxes change with and without aerosols, but a more climatically relevant quantity is to consider the daily mean aerosol direct radiative effect. And the basic premise of this is that we consider a 30-minute time step across the day, considering the solar zenith angle. So here we have the solar zenith angle for the given day, January 28, 2013. And then at each of these 30-minute time steps, we find the aerosol and cloud observation and the solar zenith angle to get the instantaneous aerosol direct radiative effect, and then integrate across the day and divide by 24 hours as represented in this equation at the top. So then we can get the daily mean all sky aerosol direct radiative effect for this given day, and then apply it for the entire time period to get one daily mean for each day. So when we apply it to the entire time period, here we have a time series of the daily mean in black and the monthly mean in red for the TOA on the top and the service on the bottom. And then we can further aggregate by month to get a sense of the seasonal cycle, which you see in this figure on the right here, where the black dot is indicating the monthly mean climatology, and the shading is the 25th to 75th percentile. Then we could take the mean of the monthly mean to see what the annual mean is, which is minus 2.13 watts per meter squared for the all-sky aerosol direct radiative effect at SGP. Some other features of note is that the aerosol direct radiative effect is stronger or more negative in the summer and weaker from October to February. And this is largely following the seasonal cycle of AOD, which is larger in the summer and weaker in the winter. And then this is further enhanced by the solar insolation seasonal cycle. So now comparing the all-sky aerosol direct radiative effect from the previous slide to the clear sky aerosol direct radiative effect from the first part of this project, by overlaying the clear sky monthly mean in blue here, we see that in general, the all sky aerosol direct radiative effect is weaker than the clear sky aerosol direct radiative effect. And this is expected since the inclusion of clouds increases the albedo and overall weakens the aerosol direct radiative effect. And then some other features from the seasonal cycle and the aerosol direct radiative effect can be understood by looking at the cloud radiative effect seasonal cycle here, which is stronger in the springtime, which corresponds to an increase in the weakening between the clear sky and all sky. Another factor is that the cloudy sky AOD is larger than the clear sky AOD, and a larger AOD corresponds to a strengthening of the aerosol direct radiative effect. However, the clouds is still a dominant factor, and overall the all sky is weaker than the clear sky aerosol direct radiative effect. We also quantify the uncertainty estimates in the aerosol direct radiative effect by considering the measurement uncertainty in the aerosol optical properties, the surface albedo, as well as the cloud uncertainties. And the total relative uncertainty is 25%. And then when we start looking at the individual terms, we see that the cloud uncertainties is this overall small contribution, as each term is 2% or less. And this is smaller than the uncertainty due to aerosol optical properties and surface albedo. And now comparing the all sky uncertainty on the left to the clear sky uncertainty on the right for their overlapping terms, we see that in general they have a similar uncertainty. It's within about 1% or so, except when comparing the uncertainty due to the single scattering albedo, where the all sky uncertainty is relatively larger for the single scattering albedo than it is for clear sky.
You're at 12 minutes, Kelly.
Cool, yes, I'm on my summary slide. Yeah, so with that, like just to summarize, so the TOA annual mean all sky aerosol direct radiative effect was minus 2.13 watts per meter squared at SGP. We also compared modeled surface downwelling fluxes with observed inputs and compared those with the surface radiometer observations and found overall agreement. And then we also did all sky uncertainty estimates and found that the single scattering albedo uncertainty is larger for all sky than it is for clear sky. So thank you for your attention.
Okay, thank you very much, Kelly. Very, very nice. Do we have any questions?
Yes, so the first one is, because you use Aeronet SSA, did you use aerosols just coming from smoke?
No, it's not just from smoke. It's we use like their data product and then match it to like the closest in time. And it's not just smoke. We actually did like a match of the aerosol type. And I can't quite remember exactly what it was for SGP, but it was closer to continental with a little bit of biomass burning to get to the right absorption.
Great, and then the next question is, did you perform any in situ measurements for validation?
No, we didn't look at any of the in situ observations, but that would definitely be like a future thing to bring this all together.
Great, I think that's it for questions.
Okay,
thank you.
and
Oops, go ahead.
oh, I just had one. I don't know if we have time. I think maybe just a little
Yeah,
bit of
one
time.
quick one. We can do a quick one.
Okay. This is, did you perform any in situ measurements for validation?
Yeah, that was Lauren's question as well, but no, we didn't look at any of the in situ observations, but that would definitely be interesting to look at to sort of validate sort of what the actual aerosol types are and their properties.
Great, thanks. Just want to say very nice talk to Kelly. And that person, Grissa, also gave a reference. So I hope we get a copy of these questions to share at the end. So thank you. Thanks, Kelly.
Okay. Yeah, thank you.
Okay, so the next talk is going to be by Michael Todd, who is from Chemical Sciences Laboratory and Ceres, and it's baseline balloon stratospheric aerosol profiles. Go ahead, Michael.
Okay, thank you. So today I'll talk about my project that's been going on for the past couple of years here at NOAA, involving both CSL and GML. First, I'll point out and thank all my coworkers listed here. There were a couple of presentations yesterday about the work my colleagues in GML are doing regarding ozone and water, and today I'll talk about how we're hitching a ride on their balloons with our particle counter and give a glimpse into some of our early data and interesting things we've seen so far. Now, I don't likely need to convince most of this crowd of the importance of aerosols, especially after Kelly's talk just now. But briefly, there's a large amount of interest in stratospheric aerosol, in particular, their effects on Earth's radiation budget. Our goals are to expand the record of stratospheric aerosol background levels and to help reduce uncertainty, validate satellite measurements, and observe changes to the atmospheric aerosol background, for example, from volcanic eruptions, wildfires, or potentially anthropogenic sources. With all this in mind, I'll introduce the BSAP project, which stands for Baseline Balloon Stratospheric Aerosol Profiles. As you may know and heard about yesterday, in GML, they've been launching ozone and frost point hygrometer sondes for over 40 years. For the last 2 years, we've been adding our portable optical particle spectrometer, or POPS instrument, to the payload. I'll note here that there's a long history of experiments from Wyoming with balloon-borne optical particle counter measurements. There are some differences in the instrumentation, but I see these as complementary and expanding the range and current knowledge of stratospheric aerosol. One of our goals, as I mentioned before, and in fact, one of the sources of our funding, is validation of the SAGE 3 experiment. Again, there was a much more in-depth discussion of SAGE 3 yesterday, so I'll simply say the data we're collecting will be used to compare our vertically resolved aerosol concentration and size distributions to vertically resolved SAGE measurements of aerosol extinction at multiple wavelengths. Much of the data we're collecting will be available through NASA as well as archived here at NOAA. Okay, for anyone not familiar with the POPS instrument, or the Portable Optical Particle Spectrometer, this is an instrument that was developed in our lab a few years ago and is now licensed to and manufactured by Handic Scientific. And that's a company here in Boulder. It's a partially 3D printed, low weight, low power consumption, and low cost optical particle counter, which we're using to measure aerosol particles from 140 nanometers to 2.5 microns in diameter. A few modifications to the original design have been made, which is found in the reference here. These modifications have been made to help our measurements at high altitude by increasing the flow rate at low pressures and some modifications to the internal airflow. If you want another example of how we're using the POPS instrument in ground-based measurements, I'd encourage you to visit my coworker and office mate, Lizzie Asher, in the poster session this afternoon. Okay, so we'll go to some preliminary results that we have from our experiments over the last 2 years. Here I'm showing the total aerosol concentration vertical profiles from around 30 balloon launches since early 2019 with altitude versus total number of aerosol larger than 140 nanometers in diameter per milliliter. This figure is a bit much, I realize, so I'm going to simplify things. In addition to removing all the colors to make it easier to look at, I've also removed 8 or so of the more interesting profiles, which we'll look at more closely in a bit. But even from what I'm calling our background profiles, we can already see a few interesting things. First, there is high variability in total aerosol concentration at low altitudes. We see 2 to 3 orders of magnitude in variability in concentration near the surface. Second, there's very low variability above around 15 kilometers in altitude. In fact, at an altitude of 22 kilometers, variability in total aerosol concentration is under a factor of 2. This low variability in the lower stratosphere allows us to see changes from natural perturbations. The first of those perturbations we'll look at was the Reikoki volcano in the summer of 2019, which injected around a teragram of SO2 into the atmosphere. You can see in the thicker green profiles that between around 15 and 22 kilometers, we see up to an order of magnitude increase in aerosol concentration compared to what I'm calling our background profiles. And above 22 kilometers, concentrations quickly fall right back into the normal range. The second volcano I will mention just erupted a couple months ago on the island of St. Vincent. These profiles were collected in the last couple weeks. Again, in the thicker red lines, we see up to an order of magnitude increase in aerosol concentration in structured bands between around 13 and 18 kilometers in altitude. I'll be interested to see if we can still see evidence for this when we do our next launch in the next week or so. And one last event that I'll mention that will be familiar to everybody based here in Colorado were the wildfires that we had last summer into the fall. As we all would have predicted, ground level particle concentrations were particularly high for a month or so, as you can see in the orange. I should mention the POPS was not necessarily tuned to look at particles from fires, as the measurements depend on refractive index, which is assumed to be that of sulfuric acid from measurements in the stratosphere, but the high particle counts from the fires are striking nonetheless. Now, in addition to total aerosol concentration, we can also get vertically resolved size distributions with the POPs. We can go in and look at any given altitude and get a size distribution. Notice that we're now looking on a log normalized number concentration on the right due to the uneven bin spacing and log diameter due to me oscillations in the particle scattering response. An example of how we can use this is shown here. So this is a slice taken out of the size or the vertical profile from the Reikoki volcano at an altitude of 16.5 kilometers. And if we compare this slice to one taken from La Soufrière, the volcano that happened in St. Vincent just recently, we can see that the aerosol size distribution from the Reikoki volcano trended towards significantly larger particle diameters. Another way that we can see, we can get some similar insight is by looking at the total particle surface area density. This is an important measure for a few reasons. Aerosol surface area is more directly related to radiative forcing and is an important factor for heterogeneous chemistry. For example, its impact on ozone balance. So you can see a larger increase in surface area density from Reikoki in green, which injected larger particles than Le Soufrière in red. Finally, I'll talk about plans that we have for the future with this project. There are really three things we'd like to increase. First, the latitude range of our launch sites. Second, the launch frequency at each of those sites. And third, our altitude range. The darker red stars are the current launch sites, so here in Boulder and then also in Lauder, New Zealand. And the lighter marks are places that we'd like to launch, for example, Hilo, Hawaii, which we're planning to do in the near future. And then we're also very interested in expanding that latitude range, particularly in the Southern Hemisphere. We're also looking at increasing our altitude range by increasing the flow rate that we can maintain in the instrument to be able to get better statistics in the lower pressure regions at high altitude. With that, I know we have a few minutes left here, so I'd be happy to answer any questions. And also, if you would rather just email me or message me in Slack later, that would be totally fine too. Thank you.
Hey, thank you, Michael. Very interesting. I have a quick question. The POPs is a low-cost instrument, but it's not exactly disposable. Have you lost any on these balloon flights over the last couple of years?
Well, when they launch from, say, a lot of New Zealand and go out over the ocean, we don't expect to get those back. Here in Colorado, we've had a very high success rate of getting these things back. I've only been in the lab for since January, and we've not lost one yet. So in Colorado, we have a high success rate.
Okay, are there other questions?
Yeah, the next question is, are you planning to compare to stratospheric lidars, for example, at Mauna Loa or Table Mountain?
I would certainly be interested in doing that. I don't have any. There's a whole gamut of things that we'd like to compare to. So certainly that would be an interesting thing to look at.
I have another question, Michael. Have you thought about doing tethered balloons so you can raise them and lower them and get profiles closer to the surface?
Yeah, that is something that we're talking about. There are a number of different platforms, kind of long-term balloon launches that people are intending to do, and as you say, tethered balloon launches. So we're certainly open to all those types of experiments and are looking to expand kind of the network of measurements being done with this instrument. So yes, it's something we're talking about.
Are there any more questions?
No more questions. You see one, Kathy?
Yeah, Lauren, no questions in the GoToWebinar pane. So I think that's it.
Okay, well, thank you very much, Michael. I think there's a lot of discussion we can have in the coffee break session. At least I know I'm very interested in this, so I'll probably be hitting you up on that. Let's go to the next talk then. The next talk is by Marcela Loria Salazar and from the University of Oklahoma. And her talk is about understanding the effects of smoke aerosols on boundary layer properties and regional weather.
Are you able to see the presentation?
Yes.
Yes. Perfect. Let me go just here for a second. So good afternoon, everyone. Thank you very much for coming and listening to this presentation. I'm going to try to explain the importance of understanding and assimilating horizontal and vertical transport of smoke and the interaction and feedback with the planetary boundary layer due to local generated and long-range transport of smoke. This is an effort coming from many co-authors. I want to say thank you to all of them. And let's start as a motivation. And the last 20 years, the increasing drought conditions, especially in the Western United States, but is moving towards the entire United States, has increased the number of wildfires. And those wildfires have been emitting a vast amount of smoke. Now, what is the problem with smoke? According to different fields, so there are plenty of studies have detected that the transport of smoke has the ability to also transport microorganisms between the smoke and changing ecosystems from one place to another one. In addition, the presence of smoke will change the radiative balance and therefore photosynthesis for many plants. The human health effects, the transport of smoke from the wildfires to high population densities have shown the presence of cardiorespiratory diseases in many vulnerable populations. If we go to the transport of smoke in albedo deposition, and we had already a representation of aerosols and changes in albedo microphysics. we add the changes of vegetation, the changes in the climate relative forces, and the presence of smoke in cloud microphysics can change precipitation patterns and therefore changing microphysics. Therefore, understanding the transport of smoke is a relevant topic for many agencies. To understand this, I'm showing here in this panel like different fires ranging from 2013 until last year, and we can see that local generated smoke can just be transported from few kilometers to thousands of kilometers over synoptic scale patterns. Satellite retrievals of aerosols has been really important to try to understand how smoke can get transported. However, like satellite retrievals are literally a camera taking two-dimensional pictures of the smoke, while if we compare the difference between what happened at ground level in a time-lapse camera, we are able to see the vertical extent of the smoke. So in comparison with the two satellite image where we can see the horizontal extent of those two fires, with respect of what happened actually in the atmosphere, we are not able to capture the three-dimensional phenomena through the satellites. So that makes inaccurate chemical transport models, air quality forecasting models for smoke. Therefore, the motivation, as a motivation for this talk, we are going to try to explain you new algorithms for plume injection height, and we use different sources of evaluations through ground-based observations, LiDAR observations. We use Calliope satellite to try to evaluate plume injection height products coming from satellite retrievals. In addition, and the most important part from those retrievals is trying to create applications. So we use instrumentations and models for planetary boundary layer, and we try to compare and understand where the smoke is in the vertical column in the atmosphere. And finally, with preliminary results, we are going to try to understand the behavior of the planetary boundary layer using statistics over smoke-free and smoke periods. As a broad impact, we will be able to improve the understanding of health effects and try to create new air quality missions from satellite retrievals to try to mitigate health effects exposures and try to understand impacts on climate change. About this research, most of this research has been already published on JGR, and it was featured as a research spotlight by the editors of the JGR journal. Let's start. Why do we need plume injection height products? So as you heard, using different satellite platforms from polar orbiting to geostationary satellites, there are multiple aerosol optical depth algorithms that they have been evaluated, and they are becoming more functional and accurate through the time. What is the problem with aerosol optical depth? Well, it's a measure of the columnar integrated amount of pollution, but it doesn't give us any information about what happened and the vertical extent. So these new retrievals for plume injection height, it will let us know in a daily time scale where the aerosol reaches the maximum amount, and they are derived for volcanic emissions and also for smoke heights. So what is the difference? Now we are able, like we can see in this AOD pattern, now to spot where we have high concentrations of aerosols. And in this case, in this panel, we are able to see how high those aerosols are able to reach the atmosphere. Now, what is the problem with Calliope? Because I usually get this question. Well, Calliope has issues, as mentioned before, I think it was Kelly, about the accuracy when we have low levels of pollution, and also the spatial temporal variability is really low. With respect to these new products, we are able to increase the spatial and temporal resolution of the observations to be more functional for forecasting events. Now, an application and an evaluation. So we use observe and model planetary boundary layers that we already evaluated in the paper, and we created this ratio. We get the plume injection height, and we divide it by the planetary boundary layer. If that ratio is smaller than 1, it means that most smoke is within the planetary boundary layer where life develops. Therefore, we are able to smell that smoke and our health will be on risk by that moment. While if that ratio is larger than 1, it means that it's a more columnar integrated phenomenon. Therefore, the smoke can reach the free troposphere. So we use, and in this case, I'm just showing you 2 examples of how we evaluated. We took an MPLNet Trinidad Head NASA LiDAR on a very complicated heterogeneous vertical aerosol profile. As we can see here, here is the development of the smoke, and here is the plume injection height retrieval over California, Northern California. Then we took another fire event over the Ring Fire, and we have a more homogeneous vertical profile for pollution. In both of them, the plume injection heights from satellite retrievals are able to diagnose the fire plumes within 200 and 400 meters with respect ground-based observations and also with respect to CALIOP. Now, the application is coming here. We use WRF-derived plume injection height, and we use it with the satellite retrievals, and we try to understand what happened over the morning and what happened over the afternoon. So over the morning overpass, we are in the presence of 2 phenomena. The first one is related to the natural thermal heating of the Earth, and the boundary layer is over or shorter, that is not fully developed. In additional fire behavior over the morning, we have less wind conditions, therefore the fire hasn't developed fully over the time of the day. Therefore, as the plume injection height increases, but the planetary boundary layer hasn't been developed completely, our ratio indicates that the most of the smoke is above the planetary boundary layer. While in the afternoon, when the fully development of the planetary boundary layer plus the fire behavior increase the thermal heating of the planetary boundary layer, we found that the percentage of confinement of smoke is higher over the afternoon within the planetary boundary layer. So over the morning, we are gonna see those effects of long range transport and escape from the planetary boundary layer, while in the afternoon, what we are finding is that the planetary boundary layer is able to trap the smoke. Now, because of those findings, we try to understand now the feedback mechanism between smoke and the planetary boundary layer and another weather patterns. We use another publication from the past to try to understand when the smoke, or when we try to separate when the smoke signal is above the planetary boundary layer and which is under the planetary boundary layer over a site in Reno, Nevada. When we have an Aeronet station, we have EPA, PM 2.5, we have also a LiDAR there, and we have balloon sounding and weather stations. And we use 8 years analysis when we have in every single start, our Aeronet station is letting us know that we have a fire signal. So the majority of the fire season over Nevada is represented from June, July, and August, and we did 8-year statistical analysis. So the blue lines here, or the blue boxes here, represent non-smoke moments, and then the red represent when we have smoke within the boundary layer and when smoke above the boundary layer is found. The key points here is that in June and September, we can find a statistical analysis where when we have the presence of smoke in the planetary boundary layer, the planetary boundary layer increases when with respect to the moments when we don't have that smoke. In the case of the months of July and August, we don't see that significant difference statistically. June and September are statistically less warm months. Therefore, the thermal heating of June and August makes smoke not increasing the depth of the planetary boundary layer with respect to June and September, but more we need to continue studying this For example, we need to study extensive aerosol properties like absorption to try to fully statistically understand and optically understand these results. As a summary, those plume injection height products are accurate with respect to LiDAR observations and ground-based and satellite retrievals. We combine successfully plume injection height products from satellites and WRF, and we were able to create an application for forecasting events that actually can increase the accuracy for forecasting and exposure of smoke. We are trying to develop better approximation and try to understand more heterogeneous aerosol vertical profiles. And if someone is interested on these related topics, we are looking for students. So if you are helping us spreading the voice that we are creating a program of aerosols at the University of Oklahoma, please help us recruiting students. Thank you very much.
Oh, thank you very much, Marcela. That was very interesting. I wonder, have you been in touch at all with the NOAA HRSS smoke modelers? I think they would be super interested in your work because they're always trying to figure out whether or not the smoke is confined within the boundary layer or well above it. So that's one of the things that you might want to. I can give you some information on who to contact there if you haven't been in touch with them yet.
I would love that. Right now, we try to take all the paper out, and now we are trying to do the co-producers and try to extend that to modelers in different areas. So I would really appreciate it, the contact.
Absolutely. Do we have any questions?
No other questions coming in yet.
Yes, same here. No questions coming in yet, but really nice talk, Marcela.
I really appreciate it. We are gonna continue trying to understand, and we are gonna go to the model part where we are inserting aerosols into the planetary boundary layer. We are expecting, depending if the smoke layer is above the planetary boundary layer, actually seeing depreciation of the boundary layer. And when smoke is within the boundary layer, we are expecting to see enhancing. However, climatology, the observations don't say that.
I have a quick question.
Yeah, sure.
I don't know much about this, but it seems like you have a raging forest fire and the smoke goes up, and at some point, in many cases, you get a pyrocumulus cloud above the smoke plume. How does satellites deal with that? I mean, it seems like that would be a very difficult thing to get right.
Yes, and so usually what the satellites work is over cloud-free conditions. So in the moment we have a cloud, the satellite will have a flag, and it will let you know that you have a cloud. So in that case, like when the users are like a more expert level, you can go and try to study how is that quality flag, and the user decide if who. In this case, the main question is who is dominating the optics in the atmosphere, if it's the smoke or it's a cloud. We develop an algorithm for Aeronet also, where Aeronet also filter out a lot of the fire pixels, and then we have to ask the question again on the Aeronet retrieval, who is dominated the optics in this moment to bring back those measurements. So it basically, if you are very well trained in those satellite retrievals and know how to use the quality flags, you can go and get these pixels back.
Okay, thank you. Thank you very much. Excellent presentation.
I appreciate it. Thank you very much.
Okay, so the final talk of our session today is by Cassandra Gaston at the University of Miami. She's studying marine biogenic emissions, African dust, and smoke impacts on aerosol composition and cloud condensation nuclei in the North Atlantic boundary layer. Go ahead, Cassie.
All right, can everyone see my screen and hear me okay?
Okay, thank you very much, Cassie. So let's see, James and Duncan, can you put up the logistics slide again? I mean, basically what we're going to do now is we've got a Google Meet room, and that's where we have time for some discussion, and you can go get a drink and whatever you would like to do. That's from 1335 to 1400. And the Google Meeting room link is on our webpage. At 1400, we're going to start with the lightning talks. And so we have 9 lightning talks for the aerosols and radiation sessions today. And those will be in GoToWebinar. So you'll come back to this, this venue. And then after that, 1430 to 1555 is a 45-minute block, block 1. The posters from the first block, the presenters will be there and they will be at their posters so you can talk with them. And then another 15-minute block after that. So right now, you're free to go into the chat room, the coffee break room, and we'll see you back here at 1400. Thank you very much.